Okay, so we're going to we looked at equations of lines in 2 dimensions, and now we're going to look at equations of lines in 3 dimensions. So it's very similar, not much different. Um, the vector equation now has an x, a y, and a z component, and then the direction vector would have an a, a b, and now a c component, which we can then convert to parametric equations. So we would have an x, a y, and a z. And we can also convert to symmetric equations by isolating for t, and we would have the 3 components there. There are no scalar equations or Cartesian equations in 3D because we could have an infinite number of normals to any given line in 3 dimensions. So if you can think of 3 dimension, right, I've got a line. I could have an infinite number of normals. The only requirement for normal is it has to be perpendicular, right? So if I have a normal and a direction vector, they are perpendicular. But if you think about this being in 3 dimensions, this normal could rotate around that direction vector, and we could have an infinite number of lines, right? Because now we can rotate it around in 3 dimensions. So there will be no scalar or Cartesian, is the other way we call it, for equations in 3 dimensions, okay? Okay, so for example, find the vector parametric and symmetric equations of the line, and it gives me a point and a direction vector. So it's pretty easy if I already have that information. The vector equation would be the point that it's starting at, and then we would have our direction vector. We can then put it in parametric by writing down our x component. So x starts at 3 and goes in the direction 1 times the parameter t. Y is 7 minus 3t, and z is negative 2 plus 2t. And then, of course, we can isolate for t and write it as a symmetric equation. So y minus 7 over negative 3 and z plus 2 over 2. Okay, so it's pretty simple to do if we have the point and we have the direction vector. So you're just writing them in different forms. B says find 2 other points. So there are infinite number of points that would be possible. Somebody asked me this last night. Depending on what you choose for the parameter. So think of a line as composed of an infinite number of points, right? There are millions and millions of points on the line. So there's lots of different answers. It just depends on what you pick for your parameter. I could pick a parameter of t equals 1. And so I could probably, the easiest form is putting it in the parametric. So I'm just putting in t as 1. So x would be 4, y would be 4, and z would be 0. So that's 1 point, 4, 4, 0. I could pick t equals negative 1. Maybe I'll go in the other direction. So if t equals negative 1, x would be 2, y would be 10, and z would be negative 4. Okay, so there's an infinite number of answers. Just indicate what you're using for your parameter, and you can find 2 other points. And then the sort of reverse question is checking to see whether a point is on the line. So negative 1, 19, 8. And we'll use a similar process. We're going to use our parametric. And we want to check and see if the parameter is the same if we plug in these values for x, y, and z. So we've got 3 plus 1t. We've got 7 minus 3t. And we've got negative 2 plus 2t. So what we're going to do is put in these points for x, y, and z. Negative 1, 19, and 8. And then we're going to solve for t. and then we want to make sure that the parameters are the same. If they are not all the same, then that point does not lie on the line. So the first one, t, would be -4. The second one, let's see, 12 divided by -3 is -4. And then here we would have 10 divided by 2 is 5. So 2 of the parameters are the same. One of them is different. Therefore, it's not on the line. It has to be the same for all 3 values of t. Okay, so you're just using the different formulas to answer various questions. This one wants you to find the parametric and symmetric given 2 points on the line. So if you think of your equations of these lines, we need a point. Well, we have 2, so we have 2 options for the point. We also need a direction vector. So our direction vector could be P to Q, or it could be Q to P. Keep in mind that there are always alternate answers. So I could go from right to left or left to right, right? I could go from P to Q, or I could go from Q to P. So I'm choosing to go from P to Q. So I'm taking Q, the end point, and subtracting P, the start point. And so that would be -6, 0, and 4. You could use that. You could also reduce into lowest terms. So I could divide all components by -2, which would give me 3, 0, and -2. So I could also use that. And I could use either point. So I could use starting at P in the direction 3, 0, -2, or I could say starting at Q, going in that same direction, or I could also use the direction vector -6, 0, 4. Okay, so lots of different answers depending on which point you use to start at, which direction you go. So the direction vector in lowest terms is probably the best answer, and that's probably the answer that you're going to see when you're checking your solutions. Generally, they're in reduced form, but also keep in mind that there are other answers that are fine. So I could use any scalar multiple of 3, 0, -2. Okay, and either point. So lots of different answers for that. Okay, this one says determine if line 1 and line 2 are coincident. Okay, so 2 things we need to check to see if they're coincident. Okay, number 1, they have to be scalar multiples of each other. They need to be parallel. So think of 2 lines. First thing I'm checking is, are they parallel? They can't be coincident unless they are initially parallel. Okay, so they need to be scalar multiples of each other. So you can kind of, sometimes you could just eyeball them and tell that they are scalar multiples. I can see, okay, I multiplied this direction vector by a number and I get the second one. Another way that is useful to check if they're scalar multiples is to see if they reduce to the same components. So looking at these direction vectors, it's not so easy to tell if they're scalar multiples, because I can't multiply 2 by a whole number and get -7. Obviously, I can multiply it by a fraction. But in this case, it might be easier to reduce them to lowest terms and see if we get the same components. So I'm going to divide the bottom by -7. That gives me 1, -3, and -1. So yes, they are parallel because they reduce to the same components. If I were doing an actual scalar multiple, I would say D2 is D1 times, I guess, 7/2. So if I multiplied, so for example, if I multiplied the first component 2 by -7/2, I would get the second component in the second direction line. So if you were actually doing a scalar multiple statement, D1 if I multiply D1 by negative 7 over 2, I would get all the components of D2. So that's another way to look at it. But sometimes reducing it is the easiest way. Okay, so they are parallel. They are scalar multiples of each other. So they are parallel. The second thing we want to check is, are they coincident, meaning are they the same line? Do all the points on D1 lie on D2 or vice versa? So in order to check that, we want to check a point in one line lies on the second line. Right, so if a point from line 1 lies on line 2, they must be the same line, or vice versa. I could take a point on line 2 and see if it lies on line 1. So I'm just going to take line 1. And the easiest way to check is to put it in parametric first. So I've got negative 1 plus 2t. I've got 0 minus 6t. And then I've got 2 minus 2t. And then I'm going to check the point that is in line 2 is given as negative 22, 63, and 23. So I'm going to check this point in this line and see if the parameters are the same. So the numbers I'm checking, I'll just write in here. And then we'll solve for t. Okay, so the first one would be negative 21 over 2. The second one would be 63 over negative 6, which reduces to negative 21 over 2. And then the third one would be 21 over negative 2. So yes, they are coincident. My t value, it was the same for all. So not only are they parallel, but a point on line 2 lies on line 1, so therefore they must be coincident. Okay, so that's easy to check. This is just, this one's a pretty simple one. Just write the vector. It's given in symmetric form, so you just want to be able to take the symmetric and write it in vector and parametric. So remember that each of these equals t, right? When we write it in symmetric, they are isolated for t. And so I would get x minus 4 equals negative 3t, and x equals 4 minus 3t. So there's 1. And then I would do the same with the y. That equals t, so y would equal negative 5 plus 2t. And then the z, so that is over 1, right? So if there's no number there, it means it's divided by 1. So z would be positive 7 plus 1t. Okay, you can also write it in vector form. And so the point that is on the line is 4, negative 5, 7. And then the direction vector would be negative 3, 2, 1. Okay, so just practicing going back and forth between the different forms. All right, last one. Write the equations of two lines that intersect at the point and are perpendicular to each other. Okay, so there's going to be lots of answers for this. So it has to contain this point. So I know it's going to contain the point 1, 4, 1, negative 1. Then I have to figure out a direction vector. So both of these, so vector line 1 and 2, they both have to contain the point 4, 1, negative 1. Okay, because that's where they intersect. So that's the common point. They have to be perpendicular to each other. So the direction vectors have to have a dot product of 0. There are millions of answers that you can make up. Okay, you could keep it very simple. You could keep it very simple by saying 1, 0, 0. So remember that the dot product, when I multiply the x's plus the y's plus the z's, have to add to 0. So if I do 1, let's say -1, 0, and actually, that's not what I want to do. I could pick 0, 1, 0, right? So 1 times 0 is 0, plus 0 times 1 is 0, plus 0 times 0 is 0. That adds to 0. So that's one option, keeping it simple, just putting in some 1s and 0s. And I could put the 1s and 0s in wherever I want. I could use some other numbers, okay? As long as the dot product is 0. So for example, I could say, let's make it, I don't know, 2, 0, -1. What would I multiply that by to get 0? Well, I could make that -2. I could make, I don't know, this 1. So right now I have -4 plus 0, so I need a +4, so I could make that -4. Okay? So 2 times -2 is -4, 0 times 1 is 0, and, oops, one needs to be a plus. And -1 times -4 is +4. That works out to be 0. There's another option. So you can choose whatever numbers or values you want, just making sure that the dot product equals 0. Okay, so you can keep it very simple using 1s and 0s. You can make it a little bit more trickier with putting in some numbers. But when I'm checking your answer, all I'm checking is, does the dot product of the two direction vectors equal 0? That's all I'm checking. And do they have that common point? Okay, so 1, 0, 0, 0, 1, 0 is an option, or you could go a little bit more adventurous and pick some other numbers. Okay, so always keep in mind that there are lots of different answers for some of these questions. Okay, so when you double check the answer, just think, right? I get these emails, oh, is this the same thing? So try to be proactive and sort of think, okay, if I take a scalar multiple of this, is that correct? If I reduce it, do I get the right answer? Okay, so try to take a little bit of initiative to try to figure out whether your answer is correct or what happened to the solution that is different from yours, and try to determine it that way. And then if you're still stuck, you can always ask. But a lot of times you can solve these problems by yourselves.